Okay, let's see. I was saying, as Martin was saying, the talk will be about the sleep behavior on velocity weakening barriers. This is a work that I started to work in France with Jean-Paul during the lockdown and confinement. And so now I will try to show the best results that I have and to try to make some discussion about it. So first, some quick overview. I will divide the talk into 4 steps. The first is introduction. This is some motivation, some question, and some context, background context, the methodology that we will use, some results. The methodology is divided mainly in 2 parts. That is the rain state friction that will be used to make the simulations and try to understand barriers. And then we will use fractal mechanics, the really basic knowledge, in order to understand what is happening within these barriers. So then we have at the end, the discussion and some conclusions. So very quickly, some basic idea of subduction sum that I'm interested. So in the Chilean case, for example, we have 2 plates interacting. The sonic plate that is subducting below the upper plate, or the Nazca plate subducting below the South American plate. And we have this region here, in this part here, where the plates get stuck during the interseismic period. And therefore we have elastic strain accumulation, energy accumulation. And this period can last at least decades to centuries. And of course, we have upper plate deformation due to this process. And then we have the seismic period, when the stuck area ruptures, releasing the energy in an earthquake. This is the seismic period and usually lasts like seconds to minutes. And of course, we also have upper plate deformation. So we are interested in this context and the seismic cycle. So the basic idea here is that we have 2 plates. Both plates are characterized by really complex structure. Like for example, here the subducting plate has Simon change and fracture zones, while the upper plate can have a lot of geological bodies, usually with difference in density. And at the end, the literature show that both plates can exert some control in the frictional complexity along the plane interface faults. So here in the red areas, we usually have the asperities, seismic asperities, which are zones in the interface fault that get stuck in the interseismic period and can release the energy in earthquakes. Why this is important? Because one of the reflex of this really complex structure is the segmentation and seismic pattern on subduction zone. And for example, we can see how along different subduction zones, we have small earthquakes that that area is filled by a big earthquake like Sumatra, or in the case of the south of Chile, where in the same portion is breaking and very similar earthquakes. So at the same time, we can see how the small earthquakes have a small extension compared to the full extension. So why the segments are so important was basically because the length of these segments usually are the characteristic earthquakes of those sections. It means the largest or the maximum length an earthquake could have there. And also because the magnitude of the subduction earthquakes is scaled with rupture lengths. So it's very important to try to understand what is controlling the extension of the earthquakes. And in our case, we are more interested in the alone strike segmentation on subduction zones. At the same time, some previous works, like this one that I showed you in the first seminar that I gave in Geoazur, we try to map some barriers and some segments, taking into account the covariance between different geophysical fields like gravity, locking, and friction. Well, a seismic barrier is usually a place in the interface fault where the ruptures tend to stop. okay? And we have identified several permanent and persistent barriers in the Chilean subduction zone. And very interesting things happen there. Like, for example, this case in the Maule area, where we have two historical earthquakes in 1730, 1751. So these two earthquakes are currently being investigated for a group, for a teamwork that I'm working also, but using more paleoseismology and paleodynamics data. And they are trying to understand how these possible two earthquakes overlap in such a big zone, and at the same time, they have been discussing that probably these two earthquakes are magnitude 9 or a little bit more. So if I'm not wrong, would be the first time that two 9 magnitude earthquakes overlap in such a big area. So this is really important for the people living here. As you can see, you have two earthquakes of magnitude 9 in less than 20 years. So the damage there is really high. So we need to understand the physical nature of the barriers, what controls the barrier, what is the physical happening there, and how this controls the seismic segmentation. So a brief understanding that we have here is that maybe the two earthquakes overlap along a strike, but along deep there is a small variation. So maybe 70-30 earthquake rupture just the down part of the seismogenic zone, while the 70-51 break just the upper or up deep zone. So seismic barrier, as I said, are zones where usually earthquakes tend to stop. So in order of trying to map this frictional variability along a strike, people usually use GPS data that are measuring velocities, surface velocities, and through inversion methods, they try to have an image of the seismic or the locking state the plate. So the locking basically is how strong plates are coupled. So values close to 1 say that the plates are really locked, so the elastic energy rate is really high, while the opposite happens when we have values close to 0, where creeping is the most significant way of sliding or stable sliding. So as you can see here, we have a map with a long stripe locking segmentation for the Chilean margin. And usually people have seen that some seismic barriers are characterized by low locking and therefore high creeping rates. As for example, here so I have an error here in the image, but here, for example, in the Maule area, we have that the earthquake of Maule 2010 ends in this area of high or intermediate locking. So numerical approaches also confirm this observation that seismic barrier can be characterized by low locking, but it's not always the case. And usually the barriers are said to be velocity straightening areas. So velocity straightening areas are just places where under slip we have an increase in friction, therefore promoting the arresting of the events. So we need to understand more that probably where we have high locking barriers, another frictional regime could be happening, and then velocity weakening barriers need to be explored, and it is what we are doing now with Jean-Paul and part of my PhD. So really fast and really brief part of the methodology, we will use the rain state friction. Okay, so this law that is relating stress with normal stress, some static friction, and some parameters comes from the observation that friction depends on a slip rate. So as you can see here, for example, for a jump velocity, that it could mean an earthquake or instability, we have an increase in friction, as you can see here. So for this jump in velocity, we have an increase in friction, and this is the called direct effect that depends mainly in the magnitude of the parameter A. So then when we have this peak in the friction, we have a state evolution effect, and depends mainly on the value of B. So these two parameters are really important because they are controlling how friction evolves in a point of the fault. And so from these two values, and specifically from A minus B, we have two main regimes, velocity straightening and velocity weakening. So velocity straightening is when we have an increase in friction when we have sliding on the fault, but velocity weakening is when friction decreases really fast because we have unstable sliding on the fault. So from this law and from some numerical approaches, we can have how a long time we have evolution of the stress and evolution of the slip rate in one point on the fault. So here in a zoom, you can see how is the interseismic period when we have the increase in stress and increase in slip rate. And then we have the seismic period when we reach the maximum slip rate and the maximum in stress. And finally, we have the seismic phase, the seismic period, when we have a relaxation of the stress on the fault. So with this law, we are able to modulate the seismic cycle, and it's what we are going to do. So there we have here. So in order to do that, we will use this model setup. So as you remember, we have a very complex structure along the plane, the fault plane, and usually we have seismic asperities and some seismic barriers, and the upper and down deep part of the interface are creeping via seismic slopes. So in order to modulate this, we will use the quasi-dynamic earthquake simulator. That is our contribution of Jean-Paul and a lot of students and colleagues. And we have this setting, this model setup. So we modulate seismic asperity with really velocity weakening patches, two patches, that in the middle we have a velocity weakening barrier where A minus B is negative, but it's not that much, it's 2 times less than the value of the asperity. Also, we have the two asperity with length of LA of 70 kilometers. And this system is loaded by 2 velocity straightening patches. So we run simulations making variations in the length of the barrier and also making variations with some frictional parameters that I showed in the equation before of rain state, that is normal stress and critical distance. So we run simulations with the variations of these parameters in order to understand if we can have or if velocity weakening areas can act as barriers. So another important feature here is to see or to have some basic knowledge of fractal mechanics in order to understand what will happen within our simulations. So let's imagine that we have a plane here oriented in the X direction, and we have a rupture with a non-uniform stress drop. So from this configuration, we can obtain the stress intensity factor that depends mainly on the stress drop, and also have 2 weight functions. And the purpose of these 2 weight functions first is to make that the most recently ruptured part of the event give the largest contribution to the stress intensity factor, and at the same time, the interaction, these 2 weight functions takes into account the interaction between the 2 rupture fronts. So having this stress intensity factor, we can define the static energy release rate. And so the static energy release rate is very simple in this world. The energy per unit area consumed during quasi-static drop run. So it's like the energy that we have been using to create to make the sliding of the fault. And then we have another quantity. For example, here in one point of the fault, you can see how we have the stress peak versus the slip on that point. and the area below this curve is the work required to make sliding or to awaken in the fault. And so this is the fracture energy. And the fracture energy is mainly the energy required to initiate sliding and waking the fault. So having these two quantities, we can define, or better said, it is defined an arresting criteria. And this arresting criteria is based in the ratio between fracture energy over static energy release rate. So what is saying this arresting criteria? That the larger the static energy release rate, the faster the crack will propagate. Here we have the rupture velocity, and here we have the ratio between this and this zero. So the larger the static energy release rate, the faster the crack of the rupture will propagate. Then the opposite happens when fracture energy increase. When fracture energy increase, the velocity rupture decrease, and then we have the stop or the resting of the earthquake or of the rupture. So let's keep in mind this criteria, mainly the ratio between this zero and fracture energy and this zero. So here is a little bit mistake, but when fracture energy is bigger than this zero, bigger than 1, we have the resting. So let's see the mainly results that we have here. I will show you 2 examples from the simulations. Here we have a simulation with the 2 asperities and the variability. So in blue lines, you can see the stable sliding, and in red lines, we have the earthquakes or the dynamic rupture. So in the red and in the black line is the variability located. And this is the position along the fault, along the slide, and this is the accumulated slip in the y-axis. So you see that the earthquakes are stopping all of them in the barrier. And at the same time, we have a small events in the boundary between the barrier and the asperity. So here we have the slip rate and the log of the slip rate normalized the velocity of loading of the velocity plate. And we have the same here. We have that the events marked in red lines with the epicenter in red star are stopping the barrier marked by dashed line. So most of the events are stopping, and therefore we have a permanent barrier for rupture propagation. Yes. And as you can see also, we have that the barrier is locked. So in order to see more clearly that result, we can have a locking map distribution, the same image, but with the locking, it means values close to 1, it means that the fault is really locked, and close to 0, that is creeping. So you see that the velocity restricted areas are creeping, but the barrier is mostly locked. So this is really relevant because most of the barriers are being studied and are showing that creeping is the most predominant slip pattern. But here we can see that barriers also can have high locking degree, and this is a permanent barrier. So we can ask how, if we have such a big lock in the barrier, so why we don't have earthquakes crossing the barrier? So in order to understand that, we have investigate how the percentage of slip is distributed under locking, dynamic, and transient phenomena. So transient phenomena is just a slow slip event creeps. It means that the slip rate is really low, but not below the loading velocity. And dynamic is rupture of or earthquakes. So you see here in the barrier that almost 70% of the slip, the total slip, is released by transient events. And also we have some dynamic contribution. When we see the time percentage of how much of the time the barrier remains locked, we see that almost 90% of the time is locked, but 10% of the time is with these transient events. So you see here also that we have a big change in the colors, more yellow. So we would say that most of the sleep deficits in the barrier is released as after sleep after each earthquake, but in permanent barriers. When we go to another configuration, when it's almost identical to the previous one, we have here the length of 40 kilometers, but the DC now, the critical distance is a little bit low. So we see a more rich sleep behavior. And at the beginning, you see how some ruptures can penetrate a little bit the barrier, but another can cross totally. So watching this sleep rate map, or this is sleep rate plot, you see how at the beginning, the barrier is in creep state, or is a little bit unlocked, and then in the 6,000 year, we have changed the locking state to more locked. So here we have temporary barriers. Okay, so earthquakes can either cross the barrier, triggering the rupture of the second asperity, or arrest within the barrier. So when we look the locking state, you see the same, right? That we have some more creeping state at the beginning of the cycle, and then we have locked. Despite, this is very important, despite frictional properties remain constant over time. So also you see how this event here trigger this after sleep, that late can trigger another slow sleep event in the barrier or in the asperity that change the sleep rate within the barrier and within the asperity. So temporary barriers, the coupling can vary through the cycle despite frictional properties remain constant, as I said. So let's try to understand what is happening here. The same. So you see here that almost the sleep distribution is divided in transient events and dynamic events. And half of the time, the barrier is locked, and half of the time, the barrier is creeping. So we have this dual behavior, and this will reach a sleep pattern that we can obtain from velocity weakening barriers. So also we will look the fractal energy results. So as you remember, the resting criteria was saying that when fractal energy is bigger than any static energy release rate, the barrier should stop. So in this plot, you see the fractal energy and G0 for the events measured from our simulations, and most of the events have fractal energy bigger than static energy release rate. So we are satisfying the criteria of arresting for rupture propagation. Then in this plot on the right, we have some curves that represent the theoretical ratio between fractal energy and static energy release rates. And in colors, you see the stress drop variation in the barrier. So here, the stress drop is really low, and here the stress drop is really high in the barrier. So you see that the curves are in a good agreement with our numerical simulation. And this plot is also crossed with the penetration ratio of the barrier. It means how much a rupture can penetrate the barrier. So you see that as fractal energy is bigger, the penetration length is small, and then the rupture are stopping. So also we have a dependency on the stress drop ratio between the asperity and between the barrier, as you can see in this color of the curves, and also depends on the asperity length and the rupture length, as you can see. So after seeing these results, we can have some more discussion about it. So as you remember, the locking degree of faults can be measured from GPS data, right? And we can have a map, or we can map the more locked zones along the plane fault, as in the Chilean case. Why this is so important? Because as I said, a lot of these segments are related to some places where the earthquakes past historical earthquakes are stopping, and a lot of them can show some creeping area as here. But for example, this zone here that is related to a permanent barrier in our study is related to a high or intermediate log. So there are some previous works trying to understand this, but using velocity straightened areas, and there is a particular study of Kaneko, 2010, that is said that all areas with velocity straightening friction may be the primary cause for the relative persistence of seismic rupture segmentation and asperities. Or, said in other words, regions of low interseismic coupling may reveal permanent barrier to large earthquakes. So he studied also the interseismic coupling using this equation that depends in the accumulated slip and the velocity plate and the interseismic time on a single point. So along the fault, in each point, we can have the interseismic coupling. And we take this equation and we apply it to our results. And we can measure also the interseismic coupling on the barrier and on the fault. And you see here that for the previous case that I showed of the permanent barrier in the results section, the logging here is close to 1, 2. So even that this is a permanent barrier, we have that a permanent barrier can have high logging. When we take the average logging on the barrier for all our simulations and we plot this logging degree versus the probability of rupture crossing the barriers, we have the following results. So the probability here, when it's 0, it means that the barrier is really persistent and no earthquakes are crossing it. So even when this probability is really low, the logging is really high. Of course, we have a tendency of increment, but it's really small, from 0.9 to 1. The same we obtain for simulations when we change the normal stress. So we can say that region of high logging may reveal permanent barriers also, and be the cause of seismic segmentation as our results are showing. So on another line, as you remember, we worked with fractal energy. So from dimensional analysis, considering our equations, we obtain some relationships between the penetration length on the barrier, and we obtain that this penetration length depends mainly on fractal energy and the static energy release rate of the asperity, and the ratio between the stress of the barrier and the asperity, 1 minus plus the ratio. So we defined what this gives clues about how the barrier efficiency should be. So penetration length can be taken as a proxy to the resistance of the barrier. It means how strong or how much is the resistance of the barrier to rupture propagation of earthquakes. So having these parameters, we define the lambda efficiency barrier parameter that depends mainly on fractal energy and the static energy release rate of the rupture to the square times the square root of 1 minus the stress drop, the ratio of the stress drop of the barrier over the stress ratio, the drop on the asperity. When we cross this lambda parameter with the probability of rupture breaking total or partially the second asperity with respect to those resting within the barrier, we have this relation in blue points, the simulations making variations of DC of critical distance, and in green, the simulations making variation of normal stress. So as lambda is small, the probability of crossing the barrier is high. So we have really no permanent barrier. And when the lambda is really high, we have that the probability of crossing the barrier is really low, so we have a permanent barrier. When we try to predict this curve, taking some variations of a stress drop in our simulations, we have this similar curve in red. for DC variations, and in red, in black for normal stress variations. So also we can predict this behavior taking into account the equations in the variation of stress drop with change in frictional parameters. So almost at the end of the talk, we make a review and we try to discuss how could be the tectonic control on seismic segmentation and barrier efficiency. Why? Because here, for example, we have two cases for the Southern Andes and the Central Andes. There is a basic idea or basic observations or spatial correlation that show that asperities, seismic asperities or rupture lengths tend to stop in places where we have high normal stresses, or where we have fracture zones, or where we have, for example, here a seismic change coming in the subducting plate, or when we have a starving sediment trench, we usually have a small earthquakes, or when we have a full sediment trench, we have bigger earthquakes. So there is a large community trying to study the tectonic control and seismic behavior. In our case, if we see, or if we try to understand how geological features can affect some frictional parameters as normal stress or DC change, we could support the idea of tectonic control on seismic behavior, because this geological structure could be influencing the fracture energy or the static energy release rates. So it is really important to understand how this geological structure can be influencing these frictional parameters in order to improve and to assess the seismic hazard assessment for those regions where, for example, in the Maule zone, 2 earthquakes of magnitude 9 are happening. Normal stress, for example, can be related usually, for example, here, normal stress, high normal stress is related to high density geological bodies. So having a high normal stress and considering that fracture energy is proportional to normal stress, we could say that a zone of high density and therefore high normal stress could behave as a barrier because we have a high fracture energy there. Also, the relationship between DC and geological structure is not so understood, and there are a lot of interpretations if we consider DC estimation from lab experiments or DC estimation from seismic observations. Therefore, we need to improve this correlation, that maybe we can have some relationship between DC and change in the wet sediments incoming from the trench, but it's something that we have to discuss later, and we have more speculations about it. So to end the talk, we have some remark conclusions. So first, that on faults governed by rain state friction, barriers to earthquake rupture are not necessarily velocity straightening, and we have seen that velocity weakened areas making variations on DC or normal stress can behave as either temporary or permanent barriers. Permanent barriers, permanent velocity weakened barriers, have high DC values and remain locked between earthquakes, and the slip deficit is accommodated mainly by rapid after slip. Also, we have that degree of locking within a barrier can change both between earthquakes and within each cycle, despite its friction properties are constant. Also, the barrier efficiency depends mainly on the fracture energy of the barrier and the energy release rate of the seismogenic segment. Understanding how these quantities change along subduction zone and how these are influenced by tectonic features is essential to assess seismic hazard. And finally, we have seen that as locking can change, the current image that we obtain from locking maps are not necessarily the same behavior that in the past. So current locking interpretations are not enough to infer slip behavior, and numerical results that usually people are obtaining should be crossed with paleohistorical data in order to capture the long-term big picture. Merci for your attention. Here we have some seats that the present is the key to the past, and from what has actually been, we have data for concluding with regard to what wishes to happen thereafter. So that is the last message of the talk. I hope you enjoyed, and any question I will be glad to answer it.